Let's solve 0-1 matrix. Hey everyone, this is KeyStrokes. I'm a senior software engineer at one of the FAANGs and I like to make videos on LeetCode problems and programming puzzles and anything and everything on computer science. Today we'll take a look at LeetCode's problem 542, which is called 0-1 matrix, and it's a medium level problem. We'll be discussing three different solutions to this problem. We'll start with brute force, then we'll use breadth first search, and then we'll use dynamic programming to solve this problem. So let's take a look at the problem statement. We are given a m by n binary matrix, that is, it has 0 and 1s, and we need to return the distance for each cell to its nearest 0. And it says that the distance between two adjacent cells is 1. For example, in this matrix, we can tell that this element is a 0, so its distance from the closest 0 is 0, because it itself is a 0, and that applies to all of the zeros. Now for this 1, the nearest 0 can be any one of these, so its distance from any of these zeros is 1. And so the final output is 0, 0, 0, then 0, 1, 0, and then again 0, 0, 0. Now in the second example, the distance for all the zeros remains 0. And for this one, the distance to the closest 0 is 1 because all the zeros are at a distance of 1. Similarly, for these two ones, the distance is 1. However, for this one, the distance is 2 because it takes one cell and 2 cell to reach to this 0 or any of the other zeros. So the output becomes 0, 0, 0 for the first row, then 0, 1, 0 for the second row, and then 1, 2, 1 for the third row. So let's see everything that we need to know to solve this problem. You need to know how to run for loop as the basic programming concepts. And then as for data structures, you need to know how to work on arrays and matrix. And for the BFS based solution, it's important to know on how to use the queue data structure. Okay, so let's see how we can use brute force to solve this problem. Let's say we are given this matrix, which is a binary matrix with dimension 3 by 3, and we can see all the zeros and ones in here. Then we have another matrix right here where we store the distance for each cell to its closest 0 cell. So if we iterate on the original matrix one cell at a time, we'll start with this element, and because this element is 0, I think we can just set the distance for the cell to be 0 because the closest 0 to a 0 is itself. Then we move on to the next cell, and this again will be 0 because this is 0, and then move on to the next one, and this is 0 again. So now the first row is complete. Now when we come to the second row, we look at this cell, again this will be 0, very convenient. But then we have this 1 here. Now for this 1, we can start by setting some max value, let's say 10. Now from here on, we'll go through every cell in the original matrix and compute its distance from this cell that we are working on. So first we compute the distance between these two cells. So let's see what the distance between two cells would be. So let's say the 0 is at a position x1, y1, and this 1 is at a position of x2, y2. Then the distance will be x1 minus x2 plus y1 minus y2, and we'll basically take the absolute values of these so that they're not negative. And that's the distance that we need to consider. So for this pair here, the distance will be 1 and 1, which is 2, and 2 is smaller than 10, so we update this to 2. Then we do the same thing with the next element, which is this one, and we compare these two, and this time the distance is only 1, and 1 is smaller than 2, so the distance gets updated to be 1. Now we keep doing that for each and every pair for this one, and every time we encounter a 0, we calculate the distance and see if that's a closer distance than what we already know. So we have found 1 as the closest distance, and if we keep doing that, I don't think we'll get any smaller distance than this. So after 1 is processed, we move on to the next cell, which is 0. Now again, for 0, the closest distance to another 0 is itself, so the distance becomes 0. Now we move on to the next row and we look at this item. Now we do the same thing because it's a 1. We have to compute distance from each and every cell from this 1. And if it is a 0, then we compute the distance and see if that's the minimum we have seen so far. So to start off, we initialize a max value here, which will be, let's say 10. And then we start computing the distance one cell at a time. So we start from the top left. We start with this item. The distance between 1 and 0 is 2. And 2 is definitely smaller than 10, so this 10 gets updated to 2. Now 1 and this 0 gets evaluated. This distance becomes 1, 2, and 3. 3 is greater than 2, so we don't update anything. Then we move on to the next one. Now this time it will be 1, 2, 3, and 4. 4 is again greater than 2, so we don't update it. Then we look at this 0, which is at a distance of 1. And 1 is definitely smaller than 2, so we update our distance to be 1. And again, we just keep going and keep doing this for the rest of it. In this case, the only 0 left is this one here. So if we compare the distance here, it's 1, 2, and 3 is greater than 1, so we don't do anything. And the final distance becomes 1 for this cell. Now we move on to the next cell, which is this one here. And because this is a 1, we again go through each cell, and if it's a 0, we compute the distance and see if that's the minimum so far we have seen. So we initialize it with 10 as the max distance. And then we start with the first cell, which is 0. Now distance between the 1 and 0 will be 1, 2, and 3. And 3 is smaller than 10, so this becomes 3. Now we move on to the next cell. The distance between 1 and 0 will be 1 and 2. 2 is smaller than 3, so this 3 becomes 2. Now we move on to the next one. This time it is 1, 2, and 3. 3 is greater than 2, so we don't do anything. Now we move on to the next cell. This is 0. Now the distance will be 1 and 2, which is equal to 2, so we don't have to do anything. We move on to the next one. Now this is a 1, which we don't care about, so we ignore it. Now we go to the next cell, which is 0, which is at a distance of 1 and 2, and we already have 2 as a minimum distance, so nothing to update there. And then we go to the next cell, which is 1, and because this is a 1, we ignore it. Then we come to self. Now this is again a 1, so we ignore it. And then we go to the last cell, which is a 1, which we ignore because it's a 1. So in the end, the distance becomes 2. Now we look at our final cell, which is 1. So we do the same exercise, initialize it to 10 as a max value. And if we run through the same process, we will arrive at a number as 1. So in the end, this becomes our answer, which is 0, 0, 0, 0, 1, 0, and then 1, 2, and 1. So this is how the brute force algorithm looks like to solve this problem. So this is how the pseudocode looks like for the brute force solution that we just discussed. As the input, we are given the matrix, which is m by n binary matrix. Then we create a new array called dist, which has the dimension m by n. And then we start to iterate on all the rows and all the columns. And then we check if the current cell value is 0, then the distance for that cell is basically 0. Otherwise, we start by assigning integer.max, that is the maximum distance for the current cell. And then we run a for loop again on all the rows and all the columns. And then we check if the cell that we are working on in this new loop is 0, then we compute a distance from that 0 cell to our current cell and update our distance to be the minimum of the distance we know so far and the new distance. So basically for each cell, we go through all the cells in a matrix, and if any of those cells are 0, then we recompute the distance and update our distance matrix so that we record the minimum of the distance we have seen so far. Once all the loops are run, we return the dist matrix, which has our minimum distance for each cell to its nearest 0 cell. Okay, so let's jump into our IDE and code the brute force solution. Okay, so here's LeetCode, and we can look at the function signature that we have to work on. So copying this and going into IntelliJ, let's paste this into the solution class that we have here, and let's start to work on it. So our input is a 2D matrix, and then the output we expected is another 2D matrix, which gives you the distance for each cell to its closest 0 cell. So to start, let's first see how many max rows are there, which we can store in max row. This will just be the length of the matrix. Similarly, the number of max columns will be max col, and we can just use the first row and the length of it. Now let's create the distance matrix that will respond back. So that will be new int max row and max column. It will have the same dimension because we need to return the distance for each and every cell. So let's start our iteration. So we'll start with a for loop on all the rows. So we'll start with row equal to 0 and run all the way to max row. And we'll do the same for the column. So running a for loop with column equal to 0 and running until max column. And then the first thing we'll check is if the value at the current row and column is 0. So we'll do mat row col equal to 0. If it is, then the distance that we should put for this cell is 0 because that's the closest 0 that we can get. So distance row column becomes 0. Otherwise, we can start by assigning a max value to the distance. We can do integer.max value, and then we can run a brute force where we'll compute distance from our current row and column to all the positions in the matrix. So for that, we can do another for loop. This time, let's call it row loop, which will go all the way until max row, and we'll do the same thing for column. Let's do col loop all the way until max col. And here we'll check if the current value at row loop and call loop, that is mat row loop and call loop, is 0. If it is 0, then we should compute the distance from row loop and call loop all the way to row and call, because this will be the distance for our current cell to a 0. And then we'll see if that's a smaller distance that we know so far. So let's first calculate the distance. The distance will be math.absolute row loop minus row plus math.absolute row or call loop minus call. Then all we need to do is dist row and call equal to math.min of the current value we know and the new distance that we have calculated. And then in the end, we return our distance matrix, which should now contain distances for each of the cells to its nearest 0. I have a main file here as well, where I have a bunch of base cases, what LeetCode had. So let's run this and see if this works. So yeah, we do get correct answer for the base cases. So let's copy a program and put it on LeetCode. So copying this, going to LeetCode and replacing this function and running it for the base cases, we see that it succeeds. But now let's see if we submit it and run it against the actual test cases. I won't be surprised if we get time limit exceeded exception. And yes, that's what we got. Brute force clearly doesn't scale for large matrices, so this only works for smaller matrix. So let's see how we can use breadth first search to solve this problem. The idea behind breadth first search would be to find all the zeros and then start expanding out to its adjacent cells from the 0, because at 0 we know that the distance is 0, and as we expand out to the neighbors, the distance increases by 1, and that's the best way to determine the distance for each cell from a 0, which is basically starting from our target. So the first thing we'll do is create a queue, and in the queue we'll store all of the coordinates of the zeros that we encounter. So let's start by iterating element by element in our matrix. So we start with the first element, it's at position 0, 0, and because it's a 0, we add it to our queue. So we have a 0, 0 in our queue. And as we go through the elements, we can populate our distance matrix so that we don't have to do it separately. So because we encountered a 0, the distance to the nearest 0 is 0 because the cell itself is the nearest 0. So making the distance 0 for the first cell. Now moving on to the next one, we have another 0 here. So we add it to our queue, which will be 0, 1. And again, we update the distance to be 0. And we do the same for the third cell. And here, the index is 0, 2. We add it to our queue and update the distance to be 0. And then we move on to the next one. The index is 1, 0, which we add to the queue because it's a 0. And the distance becomes 0. Then for 1, we don't do anything. And then for the next cell, again, the distance becomes 0. And then we add it to our queue, which is 1, 2. Now when we go through the rest of the ones, we don't have to do anything because they are all 1s. Now once we have all the positions of the 0 in our queue, it's time to start working on them one by one. So first we grab 0, 0 out of the queue, which is this right here. And then we evaluate its 4 adjacent neighbors, which will be this cell up here on the left and on the bottom. Now if you notice, these 2 neighbors on the left and on the top, they're out of bounds of the matrix. So we'll just ignore them. So in this case, we will only work on the right neighbor and the bottom neighbor. So ignoring what the next cell exactly is, the distance of this next cell from this cell will be 1. So 1 is a candidate as a distance for this cell. But in our distance matrix, we already know that the closest 0 that we know is at a 0 distance. Now because this 0 is smaller than 1, we don't have to do any updates and we just ignore the new distance that we found. Now similarly, when we work on this bottom neighbor, the distance again becomes 1. And because 0 is smaller than 1 in the existing distance matrix, we just ignore this value. So this was a pretty straightforward case. And after we are done with our neighbors, this 0, 0 is taken out from our queue. And now we'll move to the next element in the queue, which is 0, 1, which points at this cell. Now again, the 4 neighbors will be on the top, right, bottom, and the left. The top neighbor is out of bounds, so we'll just ignore it. Now working on these 3 neighbors, we start with the left one. Now for the left one, the distance becomes 1, but we already have a distance of 0 for this cell, so we simply ignore this one because 0 is already smaller than 1. So we ignore this distance. Now moving to the next neighbor on the right, which is this one. Here again, the distance which we evaluate is 1 between these 2 cells, but we already know that the distance is 0 for this cell. And because 1 is greater than 0, we ignore it and the distance remains to be 0. Now let's look at the fun part, which is the bottom neighbor. Now for this neighbor, the distance from the 0 is 1. And because we don't have any value here, 1 is the best distance that we have got. Now ideally when we write the program, we'll probably assign a max value here, and then we'll compare the new distance to this max value. So let's say if the max value is defined as 10 for all the cells where it's not a 0, then in this case, the distance that we get is 1. And because 1 is smaller than 10, we keep this 1 as the actual distance for this cell. Now because we updated this cell's distance as 1, that would mean we can use this value to update our next set of neighbors, as this cell now has viable information that it can propagate through to its own neighbors. So we add this 1 to our queue. The position for this will be 1, 1, and it gets added to the queue. So after all the 3 neighbors are processed, this cell is done, and then we move on to the next one. In this case, the next one will be this 0, and its neighbors will be on the left and the bottom. Now it's very obvious, for the left we'll compute the distance as 1, but we'll ignore it because we already have 0 as the distance, and we'll do the same for the bottom. We compute the distance as 1, but we already know 0 is smaller than 1, so we ignore it. And that's all there is for this cell. Now let's move on to the next cell. Here the 4 neighbors that we have is top, right, bottom, and we ignore the left because it's out of bounds. So for the top, it's pretty obvious again. The distance is 1, but because 1 is greater than 0, we ignore this one and we keep 0 as our distance. Now for the right neighbor, the distance is 1, but we already have 1 as the distance, so we don't have to update anything here. Now for the bottom neighbor, the distance is 1, but we notice that we have a distance of 10 here. So for the distance, we update it to be 1 instead of 10. And that's all there is to update for this cell. And I forgot to pop these from the queues, so we already worked on 0, 1 and 0, 2, and this was 1, 0. And also because we updated this cell's distance to be 1, now this cell has an optimized distance which it can propagate to its neighbor. So we add this cell to our queue. So this cell's position is 2, 0. So this will be a cell that will process to update the neighbors if needed. So now moving on to the next element in the queue, which is 1, 0, which is this cell here. Now we have 3 active neighbors that we can use, which are not out of bounds, the top, left, and the bottom. Now for our top neighbor, the distance is 1, which we ignore because we have a better distance of 0. Then for the left, again, we have a distance of 1, but it's the same that we already know, so there's nothing to do here. And now for the bottom, the distance becomes 1. And because we have 10 here, which is way greater than 1, we accept 1 as the new distance for the cell. And now because we updated the cell's distance, it's time to add this to our queue. So we add 2, 2 to our queue so that we can process this cell's neighbor. So we are done with 1, 2. Now let's move on to 1, 1, which is right here. Now this has 4 neighbors and they're all in the bounds. Let's start with the right neighbor. This time something will be different. Now because we know that the distance for this cell to the closest 0 is 1, the distance for the closest 0 for this cell will become the existing distance that we know of plus 1 because we have to move on to an adjacent cell. So this actually becomes 2 for this neighbor. And we're just disregarding the fact that this value is 0 because this cell is just trying to be a good neighbor and trying to tell its neighbor that, hey, I know a 0 which is at a distance of 1, and if you want to use that 0, your distance will become 1 plus 1. But fortunately, this 0 is itself a 0, and it doesn't have to update anything. So this cell basically ignores this 2 that we evaluated because its distance from a 0 is 0. Now the same happens with the top node. We compute the distance as 2, even though in this case, the distance of 1 that we have here comes from this node. So basically, we are telling this node that the 0 that you know of is at a distance of 2, and to reach to that 0, you have to go through me and then to itself, which is pretty funny. And honestly, this can be added as an optimization. If we see that a cell's value is 0, then we don't even have to do any of these checks. So this 2 gets ignored for the cell. The same happens for the left cell. The distance becomes 2, which gets ignored. Now for the bottom cell, the distance that we give out is 2 again, and 2 is definitely smaller than 10. So 2 becomes its new distance, and because we updated the distance of the cell, we add it to our queue, which is at 2, 1. And that's all that's required for this node. I know this was a very different case, and this is the basis of the breadth first search. Now 1, 1 gets out of the queue, and we move on to the next cell. Now the next cell in this case is 2, 0, which is right here. The neighbors are top and the right, and the other 2 are out of bounds, which we ignore. Now following the same strategy as before, for the top neighbor, we tell the closest neighbor is 1 plus 1, which gives us 2. But 2 is definitely greater than 0, so we just ignore it. Now for the right neighbor, it says the same thing, the distance to the closest 0 is 1 plus 1, which is 2. But the neighbor already has a distance of 2, so nothing gets updated there either. And then we are done with 2, 0. Now we move on to the next one, which is 2, 2, which is right here. It has 2 neighbors again, just like the previous case. It tells its top neighbor that the distance is 1 plus 1, which becomes 2, but 2 is definitely greater than 0, so this distance is not accepted. And it tells its left neighbor the same thing. The distance to a closest 0 is 1 plus 1, which is 2, but the neighbor already knows a 0 that is at a distance of 2, so nothing happens there. And so that's all that's required for 2, 2. Now we move on to the last cell of our queue, which is 2, 1, which is right here. Now this one has 3 neighbors, and this neighbor now tells, hey, I know of a 0 that is at a distance of 2, which will become a distance of 3 for you because it's 2 plus 1, which is 3. And we tell that to all of the neighbors that there's a 0 which is at a distance of 3, but each of these neighbors know a 0 that is at a distance of 1, so they just ignore this distance and nothing gets updated. And you can see how quickly towards the end, none of the nodes were useful as the distance matrix was already optimized pretty well. And now this is our final result of the distance matrix, where each cell shows the distance to its closest 0. So here's the pseudocode of the solution that we just discussed. It seems very dense, but trust me, it's pretty simple. So this is our input matrix that we were given, which is m by n binary matrix. Then we create a new dist array of dimension m by n, where we store our distances. Then we create this directions array, which has 4 elements to it, which indicates what direction we need to consider. So for a given cell, -1, 0 means 1 row up and in the current column. 1, 0 means the next row, but in the current column. 0, -1 means in the same row, but in the previous column. And 0, 1 means in the same row, but the next column. So for a given cell, these are the offsets of the 4 cells adjacent to it. So we start by creating a queue, and we run a loop on all the rows and all the columns of the input matrix. And we check if the cell is 0, then we add that cell position to our queue. It's basically we're making a note of all the 0 cells that we have in the matrix and we add it to our queue. And then because it's a 0 cell, it's obvious that the distance for that cell will be 0. Now, after this loop, once we have all the zeros accumulated into our queue, we run a while loop until the queue doesn't become empty. And then we pick the first element from the queue, store it in these 2 variables, which indicates the row and the column that we are working on. And then for all the 4 directions, that is all the 4 adjacent cells to our current cell, we calculate what the neighboring row and column would be by adding the direction to the row and column we are working on. Then we just make sure that the neighboring row and column are still in bounds of the matrix so that it's not going out of bounds. And then we calculate what will the new distance be for this new adjacent cell that we have. And that will basically be the distance of our current cell plus 1, because the distance between any 2 cells is 1. Now we add a simple if check. If the distance of the neighbor that we know so far is greater than the new distance that we just calculated, then we should definitely update our distance for the neighbor to this new value that we found. And because the neighbor's distance has been updated, we should add the cell position of this neighbor to the queue so that we can cascade that update to all the adjacent cells of this neighbor. And once we run out of cells in the queue, our distance matrix is up to date and we can simply return it. I hope that wasn't too confusing, but if it was, then I think jumping into our IDE will clear all of that confusion. So let's jump into our IDE and code this out. Okay, so here we have LeetCode, and this is the function signature that we have to work on. So I'll copy this into IntelliJ. We have a solution class here, and I'll paste it right here. So we have a 2D matrix as the input, and we need to return back a 2D matrix. So the first thing we'll do for breadth first search is to determine the directions towards which we can move. So let's store that in this another 2D matrix, and let's call it all directions. And there are basically 4 directions we can work on. So first is towards the top. So we go 1 row up and we do not change our column. So we leave it as 0. Then we can go 1 row towards bottom. So we make this as 1. So the first value here indicates what value should we add to our current row to either move 1 row up or 1 row bottom. Similarly, the second value indicates what value we should add to our column to either go towards left or right. So this is top, this is down, then we'll have 2 more, which is left and then a right. So for left, we'll keep row as the same, but we'll do -1 to go towards our left, that is -1 on our column. And similarly, to go towards right, we'll add 1 to our column and nothing to our row. Then let's make a note of the maximum row and max columns that we have. So we can do mat.len to get all the max rows we have. Similarly for max column, we can just use the first row's length. Now let's create our output matrix, which will be distance. It will be a 2D array, and we can do new int max row and max column. So in breadth first search, the first thing we should do is create a queue. So we can do queue of integer array, and this will basically store the position of a cell in a matrix. So this integer will contain two elements, the row and the column position, and let's call it queue, and let's use the linked list implementation for it. Now let's run a for loop on all the rows and column. So row equal to 0 all the way until max row. Let's do the same thing for the columns, call 0 all the way until max column. And then the first thing we'll add here is to see if the current value at this row and column is 0. If it is, then we add it to our queue. So we can do queue.offer, the new int, and then add our row and column to it. And because the cell is 0, we can proactively update our distance to be 0 as well for the cell. So we can simply do row and column as 0, because this is the closest we can get to a 0, because the current cell itself is a 0. Otherwise, we'll just set the distance to be some max value. So we can do integer.max value. But in this case, we are doing a breadth first search. So let's say if our neighboring cell is max value itself and we try to add 1 to it, it will cause an overflow. So we won't exactly use max value, but use a value a little less than that. So we'll just simply do minus 100,000 just so that we don't cause any overflow. Okay, so after this loop, we have identified all the 0 cells in our matrix, added them to the queue, and updated our distance matrix accordingly. Now let's start polling on our queue until it becomes empty. So we can do while queue is not empty. We'll keep running this loop. Now in here, let's first extract the pair from the queue. So for that, we can do queue.poll, and then let's get the current row and the current column. So we can store that in current row as pair 0, and the current column will be the first index, and we'll store that in current call. Now we'll go through each of the directions that we can go from our current cell. And for that, we already created the 2D array on top. So we'll just iterate over it. So for final int direction of the directions that we created on the top right here. So we start iterating on it, and then we compute what the target row should be. That's basically who our neighbors are. So target row becomes current row plus the first index of the direction, as that indicates the offset we should move for the row. And we'll do the same thing for the column. So target column equal to current column plus direction first index of it. Now we know what neighbor we are working with, but the first thing we'll do is to make sure the neighbor is within the bounds of the matrix. So we'll do target row is greater than equal to 0, and target column is greater than equal to 0, and target row is smaller than the max row we have, and do the same thing for the column, that is target column is smaller than the max column. And let me just break this down so it looks better and more readable. So if the target row and target column are in the bound, then the first thing we should do is compute our new distance for these neighbors. So we can store that in this distance variable, and the distance will basically be distance of our current row and current column, and we'll just add 1 to it because our neighbor is just one distance away from us. So if we know that a 0 is at a distance of this, then for neighbor it will be +1. Then we can do if the known distance for the target row and target column is greater than the new distance, then basically the distance should be updated for the target row and the target column. So we update this to be distance. And because the target row and target column's distance was updated, it needs to be cascaded to its neighbors. So we add this target row and target column to our queue so that it can be processed and so that it can update its neighbors. So we can do new int and target row and target column. And then in the end, we just return the distance matrix that we created. So here I have a main function with some of the base cases. Let's run it for these and see if our program works on them. Yes, it says they're all correct answer. So let's copy this whole thing and paste it on LeetCode. So copying the whole method, going over to LeetCode and replacing what we have here and running it for the base cases first. Okay, so the base cases were accepted. Now let's actually submit this for the real test cases and see if it works. And yes, this was successful and our solution was accepted. So let's make this more fun and see if we can use dynamic programming to solve this problem. We have this given matrix on the left with zeros and ones, and then we create this matrix on the right with the same dimension, and we'll try to find distance for each cell to its closest cell with a value of 0. So to start with, let's go through each of the index, and if the value is 0, then obviously the distance will become 0 for that cell. Otherwise, if it's 1, we'll just put some high number in there. So going through each of these cells, we start with a 0, the distance becomes 0. For the next one, it's a 0 again, so 0 and 0, another 0, another 0, which is a 0. This time we have a 1, so let's put a max value of 10, let's say. Then we have a 0, which becomes a 0, and the next 3 are 1, so we put 10 for all of these. So the idea behind this is that we compute the distances in 2 passes. Each cell tries to compute its distance, assuming that its neighbor has a correct distance. So in this case, if we take the example of 10, and if its neighbors have the correct distance, it will get 0 plus 1 from the top neighbor, which is 1, 0 plus 1 from the right neighbor, which is 1, 0 plus 1 from the left neighbor, which is 1, and 10 plus 1 from the bottom neighbor, which is 11. Now considering all of these distances, it will take 1 as the smallest distance and update its distance to the closest 0 as 1. But how can we be sure that the neighbors have the right distance? And that's where the trick of dynamic programming comes into play. We do a best effort, and then we do a first pass by computing distances towards the right and towards the bottom, assuming that the neighbor on the top and on the left have the right values. And once we do that and come all the way towards the end, that is on the last column and the last row, that's when we can be sure that the distance of this last column and the last row are correct to some extent, because they have considered all the cells in the way. Once we know that, we do this in reverse. This time we start from the bottom left and we go towards the left side and the top side and recompute all the distances that was computed in the first pass, because now we have new information how the distance looks like when we do a first pass through all of the cells. And once we do that, basically we run a pass from the top left to the bottom right and then back from the bottom right to the top left. That's when we get the right distance. So let's see how this looks like. So we start from the first cell. Now first cell doesn't have a top neighbor or a left neighbor, so there's nothing to do here. It keeps 0 as its distance. Now for the next cell, it looks at its top neighbor, again there's none, but it looks at its left neighbor, for which the value is 0. Now 0 plus 1 as the distance between the neighbor, it gets the distance as 1 from its neighbor, which is clearly greater than 0, so it doesn't take this value. Now moving on to the next cell, it has no top neighbor, so there's nothing to do there, and so it takes a look at its left neighbor and it gets the same value as 0 plus 1, but 1 is greater than 0, so it ignores this distance. Now moving on to the next cell here, it doesn't have a left neighbor, so nothing to do here, but it takes a look at its top neighbor and the distance is 0 plus 1. Now again 1 is greater than 0, so it doesn't take this value. And now moving on to the next cell, its top neighbor has a distance of 0, so 0 plus 1 gives it a distance of 1, which it gladly accepts because that's smaller than 10 that it knows already. Then it takes a look at its left neighbor and the distance is 0 plus 1, which is 1, but it already has a distance of 1 from the top neighbor, so the minimum distance still is retained as 1. Now moving on to the next one, the top neighbor's distance is 0, so 0 plus 1 gives us 1, and 1 is greater than 0, so there's nothing to do here. Takes a look at its left neighbor, it gives the distance as 1, so 1 plus 1 becomes 2. Now 2 is definitely greater than 0, so nothing to do there either. Now moving on to the next one, there's no left neighbor, so it takes a look at its top neighbor, the distance is 0, so 0 plus 1 becomes 1, and it keeps that distance. Now moving on to the next one, takes a look at its top neighbor, it gets 1 plus 1, which is 2, and it gladly keeps that distance, and it gets the same thing from its left neighbor, which it gives it as 1 plus 1, which is 2, and we already know 2 as the minimum distance for this cell. Now we have the last cell, its top neighbor gives a distance of 0 plus 1, which is 1, it happily keeps it, and when it takes a look at its left neighbor, it gets 2 plus 1, 3, which is greater than 1 that it knows of, so it ignores it. So this was the first pass, and now we do the same thing but in reverse. So let me clean this up a little. Now let's run the same thing, now this time from the bottom right to the top left. So we start with this cell, it takes a look at its bottom neighbor this time, but it doesn't have any, so there's nothing to do there. And the same goes for the right neighbor, there is no right neighbor, so 1 is its distance. Now it goes to the next cell, it has no bottom neighbor, but it has a right neighbor, which gives it a distance of 1 plus 1, which is 2, but it already has 2 here, so there's nothing to update. Now this cell has no bottom neighbor, but taking a look at the right neighbor, it gives it a distance of 2 plus 1, which is 3, but it already knows a distance of 1, so it ignores it. Now it goes to this cell, it takes a look at its bottom neighbor, it gives it a distance of 1 plus 1, which is 2, but 2 is greater than 0, so nothing to do there. And for the right neighbor, there is none, so there's nothing to do there. So now moving on to the next cell, it takes a look at its bottom neighbor. Bottom neighbor gives 2 plus 1, 3 as a distance, which is definitely greater than 1, so nothing to do here. And it takes a look at its right neighbor. It gives a distance of 0 plus 1, which is 1, which it already knows of, so nothing to update there. Now going to the next cell, this bottom neighbor gives the distance as 1 plus 1, which is 2, which is greater than 0, so nothing to do there. Same thing on the right side, it gives a distance of 1 plus 1, which is 2, which it doesn't accept. And we just do the same thing for the top row as well. There's no right neighbor. For the bottom neighbor, it's 2 plus 1, 3, which is greater than 0, so it doesn't take that. For this cell, its right neighbor gives a distance of 0 plus 1, which is 1, which is greater than 0, so nothing to do there. For the bottom cell, gives a distance of 1 plus 1, which is 2, again not accepted. And for the last cell, the right neighbor gives a distance of 1, which is greater than 0. And from the bottom cell, we get a distance of 1, which is greater than 0. So in the end, this is the distance that we get, which is basically after 2 passes from top left to bottom right and from bottom right to the top left. And that's the idea behind dynamic programming. We run a first pass to try to calculate distance based on the limited information that we have. And then we accumulate that information and try to get the last row and the last column with accurate data. And then we just backtrack all the way towards top left with this new information and update the distances. So here we have the matrix as the input, which is m by n binary matrix. And then we create a new distance array, which has the dimension of m by n, where we store the distance of each cell to the closest 0 cell. Now we iterate on each row and each column, and then we check if the current cell's value is 0. If it is, then obviously the distance of that cell to the nearest 0 will be 0. Otherwise, we initialize the distance as integer.max because we just want some max value to start with. And then we check if we are not working on the first row. If we are not, then we update the distance of our current cell to be minimum of the distance we know so far of our current cell and the distance of the cell right before our current row, and then we add +1 to it because the distance between any adjacent cell is 1. So basically we take a look at the cell right above us, and if its distance +1 is smaller than the distance we know so far, we use that distance for our cell. Now we do something similar for the column. We make sure that we are not working on the first column. If we are not, then we take the minimum of the distance we know so far for our cell and the distance of the cell towards our left and add 1 to it. Now we add the condition of not working on the first row and not working on the first column, because if we were on the first row, then there is no cell really above us. And similarly, if you're working on the first column, then there is no cell on the left of us. So this whole thing runs the update from top left towards bottom right. Now once we have computed that, we do the same thing but in reverse. This time we start from bottom right and go towards top left. So in this case, we run a loop from the bottommost row and the rightmost column towards the topmost row and the leftmost column. And then we add similar checks like before, but in this case we check that if it's not the last row, then we update our current cell's distance to be minimum of the distance we know so far and the distance from the cell right under us, that is in the next row, and add 1 to it. And again, we add 1 because the distance between any adjacent cell is 1. We do the same for our column. If you're not working on the last column, then we update the distance of our current cell to be minimum of the distance we know so far, or to the distance on the right of our cell +1. So after we run the updates from top left to bottom right, and then from bottom right back to top left, our distance matrix then contains the distance for each cell to its closest 0 cell. Okay, so that was a lot. I think when we start to code this out, it might make much more sense. But if you have been liking my explanation so far, then please don't forget to like this video and to subscribe to my channel. And please show me your support by buying me some coffee. And I offer one-on-ones where I can guide you on how to code, help you prepare for interviews, provide consult on project ideas and execution, and really anything and everything about computer science. If that interests you, then please find the link to this form in the description. So let's jump into our IDE and code this out. Okay, so here's the function signature that we need to work with on LeetCode. Let's copy this and go onto our IntelliJ and paste this in our solution class. So we have an input 2D matrix and we need to respond back with a 2D matrix where the value for each cell represents its distance to its nearest 0 cell. So let's first start by making a note of the maximum rows we have. So max row becomes mat.length, and similarly for max column, we'll take the first row and take its length. Then let's define what the max distance can be for a cell. So we can do max distance is equal to integer dot max value, but here we'll subtract some value, let's say 100,000, as when you work through values, we'll be adding value to the currently known distance. If the currently known distance becomes integer.max value, then adding 1 to it will cause an overflow. So we'll just subtract some constant value from it just to avoid that issue. Let's also create our distance matrix that will respond back with. Let's call it dist, and let's do new int of max row and max column. Now let's start our loop on each of the rows. So we can do row equal to 0 all the way until max row and row plus plus. Let's do the same for our columns. So call, max call, and call plus plus. Now we'll check if the current value in the matrix for the row and column is 0. If it is, then clearly our distance for this row and column should be 0 as well, because that's the nearest 0 that we know of, which is itself. Otherwise, we'll update the distance to be the max distance, and then we'll do our first step of dynamic programming, which is update the value based on the top row and the left column. And that's because this loop already runs from the top left all the way to the bottom right of the matrix. So we'll add a base case first. We need to make sure that we are not working on the first row. So if the row is greater than 0, that is, we are in the first row at least, then we can do distance of row and column to be math.min of the distance we currently know for this row and column, and look at the row above us, that is row minus 1, and add 1 to its distance, because the distance from the row above to the current cell is 1. So let me break this into multiple lines so it's visible. So this updates the distance to be minimum of the current distance that we know and the distance known by the neighbor on top of us and plus 1 to it. We'll do the same thing for the column. So if column is greater than 0, that is, we are not working on the first column, then the distance for row column becomes math.min of distance that we know for the current row and column, but this time we keep the row as constant, and instead we look at our cell on the left. So we do column minus 1, and then we add plus 1 as usual to account for the distance between us and the cell on the left. So this is all that's needed to do the iteration from the top left to bottom right. So that's the first pass. Now we need to add a second pass that starts from the bottom right and goes all the way to the top left. So for that, let's do another for loop. So for row equal to, this time we'll start from max row minus 1, and we'll go all the way until the 0th row, and then we'll do row minus minus. We'll do the same thing for column. So call equal to starting from call minus 1 and until call is greater than 0, and column minus minus. And I'll copy these if statements because we are going to write very similar statements right here. So now we need to make sure that the row that we are working on is not the last row, and the last row is max row minus 1. So this ensures that as long as the row is less than max row minus 1, we can work on it. And just like before, we update our distance known for the current row and column to be min of the current distance that we know. And this time we take a look at the row below us. So we simply do a plus 1 to the row and plus 1 to the overall value to account for the distance between us and the neighboring cell on the bottom. Now we do the same thing for the column. We'll make sure that we are not working on the last column. So call is smaller than max column minus 1, as max column minus 1 is the index for the last column, and we have the same updates, but this time we do column plus 1. And just to reiterate, we add these because we are taking a look at the next row and the next column, so we don't want to be on the last row and the last column, otherwise it will be out of bounds. So once we do this, this completes our pass from the bottom right going towards top left, and that should be all. And in the end, we just return our distance matrix and our program should be complete. So here we have the main class with some of the example base cases. Let's run it for them and see if it works. And yes, we see correct answers for all of the base cases. So let's copy this and put it on LeetCode. So copying this whole function and going to LeetCode and pasting it right here and running it for the base cases that we have. And it passes for the base cases. Now let's run it for the actual test cases and see how well it performs. And yes, our solution was accepted by LeetCode for all of the test cases. Okay, so that's all I had for this video. If the explanation was helpful, please don't forget to like this video and to subscribe to my channel. And you can follow me on Twitter. You can show me your support by buying me some coffee, and feel free to reach out to me if you'd like to have one-on-ones with me. I'm working on the next video that'll be coming out soon. Until then, try out this problem that you see on your screen. You might have fun solving it. Well, thank you for joining in. I'll see you next time.